I am 1.72. Well, that statement does not make any sense, or does it? It does not convey any information to you. I am 1.72. I've only given you three numerals, the numeral 1, the numeral 7 and the numeral 2. If you combine them, I've given you a number, 1.72. But still, that doesn't tell you anything about me. Let's start again and say, I am 1.72 meters. This now conveys information because I've given you a dimension. I've given you the dimension length. I still haven't conveyed everything you might want to know because I might be 1.72 meters wide, or I might be 1.72 meters tall, or I might be 1.27 meters thick. But I've given you a dimension. This concept of dimension is very important in physics because all quantities, like length, like width, like thickness, have a dimension. It is very important to distinguish the three terms quantity, dimension, and unit. The term quantity in physics represents a measurable natural property such as temperature, velocity, or height. That is a quantity. The term dimension, as just discussed, denotes what type of quantity it is. Height has a different dimension from weight. Width, diameter, and height have the same dimension. They all have the dimension length. Weight has the dimension force. Temperature has the dimension temperature. The term unit, that is often confused with dimension, represents, however, the unit graduation in a measurement. It relates to the measurement of a quantity. The unit graduation in a measurement system, that's represented by the term unit. Many different measurement systems exist. For example, the dimension length may be measured in units of millimeters or meters, as we just did, feet, or even inch. These unit graduations are based on different systems of measurements, and one has to make a decision which system of measurement to use. Then the unit graduation and the unit is determined. But unit is different from dimension. The fact that every physics quantity has a dimension can be exploited in dimensional analysis. Let's look at this example of a frustum, a section of a cone. And if we draw this, we can define an upper radius r1, a lower radius r2. We can define a height, and we might have a textbook that tells us about the geometrical properties of this frustum. For example, the total circumference of the two flat surfaces, or the volume, or the area of the curved surface. And the textbook might give us three equations. How do we know which equation is what? Which equation tells us the volume? Which equation tells us the total circumference of the flat surfaces? And which equation tells us the area of the curved surface? We can work this out using dimensional analysis. Looking at the algebra of the first term, we realize that r1 plus r2 in bracket has the dimension length, and the square root of h squared plus in brackets r2 minus r1 squared has also the dimension length. Length times length is the dimension length squared. So the first term has the dimension length squared. That is the dimension of an area. So this first term represents an area. This is properly the area of the curved surface. The second term has the dimension length. r1 is added to r2. That is the dimension length. So this is the circumference. And finally, we have r1 squared plus r2 plus r2 squared in brackets. That's the dimension length squared, but there is also an h in front of it multiplied with the bracket. So here we have the dimension length cubed. So this is likely the volume. You may wonder what the dimension the factors 2 pi or pi have. They are numbers and have the dimension unity. Some quantities in physics also have the dimension unity. They do not have a unit. We call that dimension unity. Typical examples are ratios of quantities. Dimensional analysis can be successfully applied to predict or verify the relationships between quantities. A classic example of that is Galileo's experiments on the inclined plane. Here the component of gravity parallel to the plane increases with tilt angle, but it is constant. One can theorize that the position of the ball x along this plane will depend on two quantities, time t and acceleration a. The question is, what is the mathematical form of that relationship? Writing generally, x, the position as a function of t and acceleration a, equals some constant, some dimensionless parameter c, times a with a possible exponent alpha, and times t to the power of beta. We know the dimensions of both sides. The position, the displacement x, has the dimension length. Therefore, the term a to the power of alpha times t to the power of beta also has to have the net dimension length. Time has the dimension time. Acceleration has the dimension length on time squared. Therefore, the beta has to be equal to 2, so that the 1 over time squared cancels with time squared, and the overall net dimension on the right-hand side is length. So alpha we can determine with this dimensional analysis equals 1 and beta equals 2. This determines the equation for the position down an inclined plane as equal to a factor of dimension unity times acceleration to the power of 1 times time squared. Experimentation can then show that the numerical value of the factor of dimension unity is equal to 1/2, and the familiar equation x equals 1/2 a t squared is obtained. Dimensional analysis has another great benefit, namely it allows you to check your numerical result. Let's say you obtain a density for your body of 7.82 kilograms per meter. You immediately see that you've made a mistake, because the dimension of density is mass per length cubed. Your result shows a dimension of mass per length. This is inconsistent.